Shiwei Zhang from Flatiron.
Thank you. I apologize for the delay. Thanks to the organizers for putting together this wonderful workshop and for inviting me. So the theme of the workshop is machine learning and quantum matter. My first impulse or inclination is to give you a summary of everything we're doing in my group. Because certainly everything we're thinking about has to do with quantum matter, and if not machine learning, at least learning by machines. Meaning I'm a computational physicist. We try to come up with algorithms to use computers to study quantum matter. But I think rather I'm going to do the opposite and tell you a very small, narrow topic focused on a few papers from last year on this particular system of the moire continuum Hamiltonian, namely worrying about the ground state phases of the two-dimensional electron gas, either just that, the uniform two-dimensional electron gas, or in the presence of a moire potential. So a Hamiltonian that looks like that with the usual kinetic energy and the Coulomb interaction with compensating background in a two-dimensional box. And then there's an external potential that's applied as these blobs, but to show that mimics a periodic structure. So when I say moire, it's actually just periodic potentials, okay? So moire potential in that sense. And these green and blue dots are electrons, and depending on how many you put in that box, there's different fittings, and this is sort of a simple model for all the exciting things that are happening in 2D materials, as you've heard from Liang and Wang already, plenty to come in this conference. So this is, in some sense, the minimum model. And what I want to focus on is what can state-of-the-art computations tell us? And in some ways, maybe embarrassingly little, but these are sort of high-level calculations that try to minimize the kind of approximations that are involved in creating these Hamiltonians. So as an outline, more technical difficulties. Okay, it's coming. Okay, so as an outline, I'm going to tell you about just the pure two-dimensional electron gas using machine learning or neural quantum state, which discovers new phases in intermediate regions, and that was sort of the thing that turned me into machine learning, made me kind of a convert, at least to look at it. And then without machine learning, but state-of-the-art computational methods to look at the phases in the presence of moire potential, in particular, a few examples: triangular lattice fitting one, honeycomb lattice fitting a half, and then a quarter, some preliminary results showing interesting new phases. And then if time permits, mention effects of the gates, which are present in structures. So new states in the two-dimensional electron gas. This is a paper that showed up just a couple of weeks ago, driven by two outstanding students, Connor Smith and Yixiao Chen. Yixiao is actually here. That says using a variational unified variational approach to describe the two-dimensional gas. So the little picture from the previous page simplifies. You have a box, you have two kinds of electrons, two different colors, and the Hamiltonian looks like that in natural units. So there's only one parameter in this problem, which is RS, the average space, linear space that an electron takes. Pi RS squared is equal to the area divided by the number of electrons. That's RS. Depending on that parameter, what happens to the electron gas? Now, theoretically, there's very, very rich, a large body of theory that talks about all kinds of states. Computationally, there's actually only two states, well, the accurate calculations that have been seen. It looks like this. So as this a function of this parameter RS, this physics is driven by the competition of two things, right? Kinetic energy term, you have an electron qualitatively confined by a linear dimension RS. So the kinetic energy scales as one of RS. And then the interaction energy is Coulomb, so it scales as 1 over Rs. So then somewhat counterintuitively, as you get the electrons closer, the interaction effect reduces. So at small Rs, you have a Fermi liquid. At very large Rs, you're going to have a bigger crystal where electrons kind of localize. And the best computations, I guess, for example, this now more than a decade old, determines that the transition from a Fermi liquid to a bigger crystal happens at about 31. And then in the crystal phase, there's possibly magnetic transition. So of course, at infinite Rs, all of these magnetic states are degenerate because it's a classical system, it doesn't care. So that's what computation says. Now, theoretically, there's theories about microemulsions, various things in here. Now, realistic systems are way out on the left at Rs of less than 10. But thanks to recent developments in 2D materials, now we can get to this region, and this makes this problem even more relevant. Now, besides that, of course, the electron gas has always served as a foundation, starting point for computations, right? In material science or biology, people use density functional theory. Well, that's parameterized based on electron gas results. So this is a fundamental model. And this work, I say the best work, happens like this, based on ugly plots that look like this. It has a separate ansatz for each phase. So for example, what's plotted here is the energy versus Rs. And you can see the different colors. For example, this is an ansatz that says it's a paramagnetic fluid. I'll explain to you in a second how you do that. And the energy, for example, here is lowest. So below here, it's a paramagnetic fluid. And then the next one, there's a little blue one that's the lowest, and that says anti-paramagnetic crystal. So that's this transition, and you see we thought happens about 31 or so, and another crossing. So that's the best sort of computation. That's how it's done. It's based on separate ansatz. So how does the ansatz work? For example, there's one that's called Slater-Jastrow. It says this: it hypothesizes a many-body wave function where R denotes the collection of coordinates of these electrons in the box. And you recognize this as a Slater determinant. So this is what our mean field theory would tell us. You make some orbitals and you put the electrons in there and anti-symmetrize them. And then this thing is a Jastrow. It tries to put in some correlations. So for example, if you put this as 1 over R, it'll say if 2 electrons are close, then there's a negative sign in the exponent, reduce the wave function sign. So that's called Jastrow. It tries to do some correlation. So that's the simplest form. If you want to make an ansatz that's a paramagnetic fluid, you would say, make plane waves in these orbitals, right? So that would be your mean field solution for a uniform system. You put electrons in, you occupy Fermi C, plane waves. For a bigger crystal, you would make these orbitals Gaussians that are localized on crystal sites. For example, you can make the width of the Gaussian a parameter, variation of parameter. And the U will be parameterized by some function. So P denotes parameters. A lot of them used to be a little because computer time was limited. So variational Monte Carlo, which has existed for a long time, favors using very few parameters so that you can minimize. You compute this wave function, the variational energy, you look for a set of P that gives you the lowest energy, and that's what's plotted here, and that decides which one gets favored. But now with machine learning, one difference really is one is still basically doing VMC, but massive amounts of people, right? Lots of people you could do. There is a refined ansatz that dates back to at least Feynman in thinking about helium-3, which is called backflow, which says, well, this determinant, the mean field thing, is not very good. You can modify this by plugging in coordinates. Instead of Ri, the bare coordinates of the electrons, you could plug in quasi-coordinates, quasi-particle coordinates, xi for Ri with a shift. Right? So the idea is that if I have electrons around me, I'm going to avoid, I'm going to move. So you put in a quasi-coordinate, plug it into this. Now you notice this is not a mean field solution anymore because it involves other particles in there. So it's actually a many-body wave function already in the backflow Slater determinant. But of course, you also have the correlation. So then you do variational Monte Carlo. Monte Carlo, because you can't compute the energy of this wave function explicitly, you have to do Monte Carlo sampling. You search for the minimum P. And then the state of the art, like this, like these things, are gotten by a next step, which is called diffusion Monte Carlo, where it recognizes that the Hamiltonian in real space that I wrote down for you looks like the imaginary time Hamiltonian looks like a diffusion equation, and then you can mimic that to do a projection. So in principle, this diffusion Monte Carlo step is a much more sophisticated step compared to current machine learning philosophically. But it's restricted by the kind of ansatz you can put in there due to what's known as a sign problem. So it's essentially exact, but limited by what, like how the best structure you can put in this. Okay. So I'm going to call this toolkit number 1. This is variational Monte Carlo plus diffusion Monte Carlo. It's sort of the current best. Right, that can do this.
So here the base, the sign structure is still given by the sleep determinant.
Yes, but the backflows.
Oh, that's okay.
So it can be better than a mean field. The energy scales, if you look at here, the error bars and so on, it's tiny, tiny, tiny. So it's very hard. And this is a challenge in a two-dimensional electron gas. It's a challenging problem. That's why you could easily go off and get wrong results. So for example, if you just did Hartree-Fock, you would predict this transition to happen at 2, not 31, but 2 or 4. So the work that I mentioned, the new neuroquantum state, now uses a single ansatz, which we call NP2 NQS. I'll explain what that means. Well, NQS is neuroquantum state, NP2, NP squared. So this is kind of on the previous page, the current ansatz. What do we need? Well, the first MP stands for message passing. It's a neural network structure. So what we're going to do is in the backflow, in here, Feynman's idea was just to linearly scale. Let's say, how far are you from the next electron? You move this one proportionally by that distance, by a linear factor. We don't do that anymore. Now we're putting a neural network on it, a message passing neural network on this backflow. And then we put, instead of this two-body correlation, of course, the actual problem is many-body correlated. We add a two-body thing to satisfy what's known as a cut, and then we add a neural network to it. So there are two message passing neural networks for the Jastrow and the backflow. And then our genius was in thinking of, in order to do one ansatz, we write the orbitals in terms of multiple plane waves, like this form. Coefficients times plane waves, and the number of plane waves is much greater than the number of electrons. So in principle, if you sum over lots of plane waves, you could produce all kinds of orbitals, including both the Fermi liquid and Gaussian, right? So we choose a large number n plane wave that's greater than n, the number of electrons, we stay with that. So that's the next P, multiple plane waves. So NP squared NQS. This is toolbox toolkit number 2. Now with this toolkit number 2, we revisit the electron gas problem. I have to say the kids pushed me. I was highly skeptical. I said, if you want to play, go play, but you're not going to beat the current thing. It's just very delicate. That was one. You can see this is what we get now. These two curves are cleaned up. What I showed you before from the previous best result. Fermi liquid is here. Regular crystal is here from the best diffusion Monte Carlo with backflow, and you see that where they cross 31. So, but this purple line is now our MP2 NQS result. And the first significant result is that you see this curve is systematically below the projected, essentially exact many-body result. This is variational, both are variational. So this is at least in the measure of energy, a better wave function now than even the projected wave function. If you compute the structure factor, you can see that it's small and then it picks up. It changes. And this is telling you that it's turning into a crystal. At a place that you can see with fuzzy, but it's bigger than what the process was. Now we can do better. We could do what's called a transfer learning. We kind of freeze the ansatz from here. We constrain it to go down in RS, and that's one curve, with the blue being the transfer learning. And then we freeze it here, go up where they cross. We can decide where the transition is. So now it detects a regular crystal automatically, and there is a revised transition point at 37. So here's what the charge density in this box looks like. Charge density, spin density. Well, for RS of 5, it's a Fermi liquid, so constant, both. For RS of 34, you see these blobs. And RS 42, you see these stripy things. This should be bothering you by now, right? I'm not seeing a crystal, but I'm seeing actually, I claim, a floating crystal. Because if you actually see a crystal, if you actually have the correct description for all three systems, you should see nothing. You should see a constant because the many-body wave function is translationally invariant. The exact many-body wave function is translationally invariant. You have a periodic box. So why do we start seeing these stripy things? So it's floating. The crystal is floating in one direction, but not both. Well, it's because when we do the calculation, we put in a fixed number of up electrons and down electrons. We fix the spin. Well, the actual crystal should not do that, right? It's going to form a triangular crystal, as I now show you. This is the correlation function. And at RS of 42, you can see the charge correlation. It forms this triangular lattice. And the spin correlation, you can see the stripy residuals. Because you give it only two colors, it just chooses what this stripy thing. So it restores translational symmetry in one direction, but not both. So back to here.
What's the geometry of your simulation?
So the geometry of that particular one I showed you is like 56 electrons or something. So it's slightly rectangular. And the reason we want to do that is because we want to make this discovery in one shot. So it's compatible with a triangular lattice. And this is the correlation function I was showing you before. On the left-hand side, Fermi liquid here. On the right-hand side, the Wigner crystal. Now we're going to focus in between here. It turns out it's a very large region, and this was the surprise. This was impressive, but okay, it revised the number. But this is what kind of sold me on the power of these structures, is that it discovered a new thing. So the Fermi liquid, if you compute the spin geobar, so the spin-spin correlation function, the Fermi liquid, you just see a little blob that, and then the rest is Friedel oscillation. I'm going to show you a line cut. In the Wigner crystal, it's this, that you're going to see the striping thing I showed you. But in between, it looks like that. It has this kind of a ring, and then it has some, I don't know, little wiggle in one direction. It breaks rotational symmetry because this is supposed to be a Fermi liquid, right? All the way up to 37, it's a Fermi liquid. If it's a Fermi liquid, it should be isotropic. This breaks that symmetry. And here the question of what the topology, what the geometry is in the simulation matters. So this is slightly elongated, so it helped it to break in one direction. We then do a square lattice. You can see that every snapshot, every optimization, it'll do the structure, but the structure will rotate randomly. But it always prefers one direction. And here's a line cut of the G of R for spin. The line cut goes like this, goes down and to the right, and this is 0. So in other words, it's asking if I'm an upspin, what is the correlation with me as I traverse? So I'm sitting here as an upspin. I want to look at the correlation of this. So this line, which is reduced by a lot, is the Wigner crystal, and you're just going to see the usual pattern. That's this triangular lattice. You can see this; these two are different directions, right? As the triangular lattice breaks. So that's why the two sides are not symmetric. And if you're a Fermi liquid, it's this gray line. The two sides are symmetric. But in between, from about 10 to 37, this large region, it just progressively goes. You can see that it goes from this gray line. One side goes down, the other side goes up, and the location approaches the Wigner crystal. So it's a marching from an isotropic correlation to a triangular, but in a way that breaks a rotational symmetry. So it's a nematically correlated spin, short range spin. Now, we need to do more. These are 56, 58, 54, or with a chuck at 120 particles. So we don't quite know exactly what happens. This is an experimental paper that's actually before. that showed surprisingly, so basically this is plotting, the top is RS. You could see that they see a Fermi liquid, but they start seeing weird stuff, which the experimental signals seem to indicate it's microemulsion, which our calculations, the signals don't seem to match. But it does match that in this wide region, there's weird stuff going on, spin kind of weird stuff going on. So it's ongoing, but this is the first thing that really hinted at some new physics that previously with the methods, the best methods, we were not able to do. So the neural network built in sophisticated backflow responses. So this, I'm showing you 3 RS of 5, 15, and 40. So bigger crystal Fermi liquid. And what I'm showing you is the red dots are positions. We're gonna put the electrons in some fixed position. Of course, this is just one snapshot of the wave function. And then we're gonna move this guy in the middle, this electron, drag it diagonally like that. We're gonna see what the backflow says, how the other particles are gonna respond. Okay? So the first one, you can see it responds in a weird way, but it's quite global. The next one in the middle, a little less. And the bigger crystal becomes very local because it really doesn't want to disturb the whole structure. Right? But you can also see that this backflow is not a linear pushback of the system, right? The whole system starts to do stuff. And that's why, you know, maybe our previous outputs was just not sophisticated enough to capture. So show you again the first one. So what I've told you about is a kind of a physics motivated NQS. Now, as neural network calculations take off in quantum matter, there's kind of, in my view, a philosophical thing that one should think through. One is the current neural network direction in other fields is massively the large language model, so massively over-parameterized. That has been, I think, primarily the direction in QS as well. We use lots of parameters. This took a somewhat different philosophy. This uses, you know, it's like a operation that goes in with the scalpel sense. This part we're going to put a neural network. The downside is that maybe you lose some generality, but the upside, the advantage is that it massively reduced the number of parameters we're trying to optimize. And as a result, these calculations were able to do 120 electrons. With that, you could do interesting quantum physics versus if it's 12 or 20, right, you're going to be limited. So I think that's an interesting question for us to think about moving forward as this field is going to move. So now I'm going to move on to add moire potential and using toolkit number 1. Some of the pioneers of thinking about the moire continuum Hamiltonian are here in the audience. So basically, we're putting back this potential, and you can add these vectors to create different topologies with the angle phi and pulling it. So for example, 26 degrees here produces a triangular lattice. And you can rewrite this just like in Jellium into a potential that is controlled by 2 things: RS, billion, well, 3 things, or RS, billion, and the depth of the potential, right? Once you decide shape of the potential. So this is using toolkit 1, a paper from earlier, beginning of last year, using 2 quantum Monte Carlo. The primary quantum Monte Carlo methods that we push in my group is actually AFQMC, which I'm not talking about. So this is using 2 methods, but I'm just going to summarize the physics of it. This is filling fraction 1, so it's sort of the simplest thing, the triangular lattice. So what we're plotting here is the depth of the moire potential versus RS. Because it's fitting 1, there's only one other parameter, which is RS. And what you see is that you have a paramagnetic metal that goes into a 120-degree nail or insulator. So there's a metal insulator transition as you cross like that. And that's in the metallic phase. This is, I think, the density, charge density, what it looks like. And you look at so this is line cuts going like that. Looking at the moire potential when you go through those cuts look like this. And you can see the charge density for the paramagnetic metal is, so this is what it is. It has response to it, but it's a much mild response. And there's no spin. And when you go to the 120-degree, so it forms, you can measure the spin, and it turns out the pattern is consistent. That's how we deduce it's 120. And the charge density is incorrect. One thing I want to comment as a side product is that be aware of approximation. So for example, here, there's already a pioneering Hartree-Fock calculations. If you did Hartree-Fock, you get this phase diagram, and you're supposed to get this. So Hartree-Fock tells you new things, right? Interesting new things. In fact, this claims it's ferromagnetic in a giant region that does not exist. And the green dots are ED calculation, exact diagonalization, meaning that you take some bands. And you can see that start to break down as well, right? The green starts to break down as well for bigger interaction. That makes sense, right? Because bigger interaction is going to mix in more bands, and the ED is going to break down. So we also checked different flavors of density functional theory, and LDA, it turns out, gives you a spurious phase as well. But what chemists like to use hybrid functions where they mix in some exact exchange. Turns out if you do 50% exchange, you do pretty well in the system. So, DFT is often used as a first check when we do experiments for theory. So this could be a shortcut that does a little better than Hartree-Fock. So this is now a paper that's from several weeks ago on the honeycomb lattice of this, so 60 degrees. And we're looking at a phase here, slightly more complicated. So the phase diagram now looks like this. This is for half thinning. And the charge, so there's basically three things is that you increase the moire potential depth. It goes from a paramagnetic metal into a ferromagnetic semi-metal, and then into a charge density. So this is the ferromagnetic metal charge density, and this is the this is the paramagnetic metal, and this is one spin now, ferromagnetic, and this is the charge density wave. Notice that it's also symmetric, but the charge density wave, if you look at correlations, it actually occupies every other one. Right? It's a charge density wave, but when you look at the density, it's going to symmetrize because it's a many-body solution, and we're going to see that. So the line cuts of the different densities. The momentum distribution here in the paramagnetic metal looks like that, but so you have a drop, right? It's a metal, and the two different directions. There are two curves shown, but they're the same, right? Two directions are the same. But if you look at this ferromagnetic metal, you look at the two directions, it looks different. One of them is smooth, the other one has the drop. It's only at the edge that it shows it's strong. And then this is the charge density wave where it speeds up. So I want to, so of course there's a lot more details, but okay, how much time do I have?
3 minutes.
3 minutes, okay. So this is a quarter fitting. It's an interesting thing using toolkit number 1, which is what I've been telling you with the moire continuum model. You would see a charge density that looks like that. So there's 2 electrons in this, show you the next one. But using NQS, you see these, every 2 electrons form this ring, and it's 2 up-down spin electrons form this ring. And it occupies it like that, which is not something that you, in the backflow DMC, or if you optimize, you would see. And it turns out we've discovered this, and then we feed the orbitals back into the backflow here. And the diffusion monopole would agree it has a lower energy, but we wouldn't have found it in the previous book. So let me just flash this. This is just thinking about the effect of, experimentally, if you have gates, metallic gates, that screens the fluid interaction. So what happens? For example, what happens to the liquid crystal transition? This is still ongoing work. But this is 1 over RS. So going from small RS to large, you go through this liquid crystal transition. But now in the presence of gates, this is the 1 over the gate separation. you're gonna have a reentrant into the fluid. So if the gates are very, very close, you screen the interaction so much, you go back to a fluid after some distance. So we mapped out this phase diagram. This is work in collaboration with this method. And then we also mapped a functional for treating these so that people who do LDA can use it. And this is important. So let me just put that back up, and thank you very much.
And the honeycomb filling one half is at the Dirac point.
Yeah.
Is that it? That's the convention.
Mhm.
Okay.
Okay, any other questions?
Yeah, so I wonder filling, what is a stable line?
So it the electrons, so there are two electrons that form a little sort of dimer that's correlated that surround this hexagon.
So it's spontaneous rotation.
It's, yeah, so, and so there's no, so you can trap, you can sort of look at every honeycomb, every site, there's two. And then sometimes depending on V, so I'm showing you an arbitrary V, there's spillage, but basically two of them with opposite spin will circle each other. And then the next two will circle each other. There's very little correlation between how they circle. That seems to be the state.
And please, Roger.
So for these microemulsions, I seem to remember that they can come with spectacularly long length scales.
Yes,
So would you even expect to see that physics at all in your simulations?
no, not with the size we're doing. I think too small. But we try to sort of see signs of this. And before, I think there's no sign of even sort of, you construct a local region and I mean, even, yeah, energetically sort of trying to analyze, piece together different regions, there's no sign. So now at least this weird thing is less contradicting possible larger domains. But no, we don't, in these simulations, we cannot see.
Actually related to that, so there is actually a simpler version of the two-back model where you just consider spinless or spin polarized electrons, where things are much simpler.
Yeah.
So the microemulsion could happen there too. So
Yes.
how much is known, and have you considered doing?
We have looked at spinless fermions as well, also too small to see.
I see.
Essentially, you see the same sort of transition, right? Because the second one is a ferromagnetic, the phase diagram I showed you, the second one is ferromagnetic. It's not that far removed from the the Viridian crystal.
And
So,
the suggestion is that you may even be able to actually measure some of the Lambda parameters by changing your geometry a little bit to force the Fermi surface to distort.
you mean at the lower RS? region?
Yes,
Yes,
in the
yes,
metallic phase.
Yes. So in fact, that's interesting. Yeah, that's there's some ongoing work on that too.
I see.
To rethink, but that's more in the Fermi field.
Yeah.
Yeah, so we're doing some of that too.
Okay, yeah, maybe let's end from here. Yeah. So we will come back in 10:30. You can have like a discussion here. Okay, so we will come back.
Okay.
Thank you.